and ask you if that point lies on the unit circle. So if you look here, does the point 1/3, comma, negative 2/3 lie on the unit circle? And you are expected to show your work. So if this is my x and this is my y, x squared plus y squared should equal 1. So if I take that 1/3, square it, plus the negative 2/3 and square it, it should equal 1. And if it doesn't equal 1, then you know it's not on the unit circle. So in this case, I'm going to get 1/3 plus 1/9 plus 4/9, which is 5/9, and that is not equal to 1. So no, it does not lie on the unit circle. Okay, so that is one type of question that I would ask you. Ananya, you can get away with not knowing the domains and ranges for this quiz. I personally like, I think the domains and ranges are important because for sine and cosine, I know that sine and cosine cannot be values bigger than 1. So if I go to question 3, where I'm asking you to find the 6 trig functions of theta, if theta passes through the point 3 comma negative 4, I'm seeing that if I were to look at this as sine theta is equal to negative 4, no, that can't happen because sine has to be a value between negative 1 and 1, inclusive. Negative 1 and positive 1 are included in those values. So therefore, I cannot just say sine is equal to my y, cosine is equal to my x. This is actually not on the unit circle. So I've got to find r at some point. Okay, so I'll go back to that in a minute. But that's why I would want to know my ranges. All right, so the next kind of question I could ask you is find the sine of 35 pi over 6. So if you think about 35 pi over 6, that's just an angle that goes around the unit circle a few times. So how does that look? Well, I know that 12 pi over 6, which is 2 pi, is 1 complete revolution around the unit circle. I know that 24 pi over 6 is 2 complete revolutions around the unit circle. And then to get to 35 pi over 6, I would have to add 11 pi over 6 more. So this angle is equivalent to saying sine of 11 pi over 6 plus 24 pi over 6. I could think of it like that because, again, 11 and 24 is hopefully 35. So I could think of it as sine of 11 pi over 6 plus 2 full periods. And we have that periodic, the periodic property that says that the sine of theta plus the period times 1, 2, 3, 4, any integer is equivalent to just the sine of that angle. So I have just simplified it a lot. And then I'm just going to find the sine of 11 pi over 6. So I know that 11 pi over 6 is in the 4th quadrant. It's a reference angle of pi over 6. And I know that sine is odd. So if sine of pi over 6 is a half, sine of 11 pi over 6 is negative a half. You don't need to know all of that. It's just, in my mind, for some reason, that's the way it works. You don't understand where the 2 times 2 pi went. The 2 times 2 pi, Adia, if I were to sketch it, this is 2 pi. This is another 2 pi. And then you have 11 pi over 6 more, which would be right there. So technically, all I'm doing is kind of getting rid of those inner spirals because my final terminal side lies in exactly the same position. So hopefully that helps. Why the 2 times 2 pi? Okay, so I'm not really getting rid of the spirals, but I'm simplifying it because it's equivalent. Okay, so on to 3. 3 asks you to find the 6 trig functions if theta passes through the point 3 comma negative 4. So I think I told you A block, the people that are here that are A blockers, and I know I told E block, that I always get 1 or 2 students, and that's when Brendan and Ethan looked at each other and said, that's me, that will say that sine theta is equal to negative 4, cosine theta is equal to 3, and then tangent theta is equal to negative 4 over 3. You will get 2/3 of the question wrong, so you don't want to do that. again, if it's not on the unit circle, you cannot say sine is equal to y, cosine is equal to x. You can only say that if it's on the unit circle. If it's not on the unit circle, it's on some other circle centered at 0, 0. So let's say that it's x squared plus y squared is equal to r squared. Well, if I know my x and I know my y, I can certainly figure out what my r is. And I gave you something easy today because it's late at night. So we have, for me, it's late at night. For you, it's not. So we have 3 squared plus 4 squared. So we're going to get 25 is equal to r squared. So r is equal to plus or minus 5, which again, we're only taking positive 5 because it's the radius of a circle. And we know radius is a positive or a distance. So we're going to get r is equal to 5. And then we can find our 6 trig functions. So our first one would be y over r. So the only difference between being on the unit circle and not on the unit circle is when it's on the unit circle, that radius is a 1, so it's over 1. When it's not on the unit circle, it's over whatever the radius is. So in this case, 5. So negative 4 over 5, 3 over 5. The cool thing is, though, if you do get this wrong tomorrow, which I would rather none of you get it wrong, you'll get tangent right, because tangent is always going to be y over x, so negative 4/3. And then just a reminder that cosecant is a reciprocal for sine. Secant is a reciprocal for cosine. And then cotangent is a reciprocal for tangent. So those are my 6 trig functions. And again, if I go back up to this cool little hexagon, my reciprocal functions are always along the diagonal with each other. And then my cofunctions, which we got into a little bit, are my functions that are horizontally across from each other. So it's kind of neat how that hexagon all works out. It is magic. Where the coordinates of the unit circle came from. Do you mean like where sine and cosine came from? Like, how do I know that sine theta is equal to y and cosine theta is equal to x? Because even though it's magical, there's a reason, a rhyme and a reason with it. I'm just waiting for your answer. I think he means square root of. You want me to tell you where those coordinates come from? Those special ones, the 30 degrees, the 45 degrees, and the 60 degrees? Oh boy. All right. Okay. So I don't have a good unit circle sketched out, so you're going to have to go with my not so great circle. It's beautiful. Okay. So if the radius is 1, right, and I am on this magical circle, and I have a radius of 1, the special angles are your 30 degree, your 45 degree, and your 60 degree angle. And the reason they're special is because of the properties that come with them and the theorems that come with them, which is that for a 30 degree angle, your short leg is always your half of your hypotenuse. So this leg is going to be half of the hypotenuse. So half of 1 is 1/2. And across from your bigger angle, that's not the right angle, your 60 degree angle is your long leg. And your long leg is always your short leg times the square root of 3. So 1/2 times the square root of 3. We simplified to just say the square root of 3 over 2. So my x distance is the square root of 3 over 2. My y distance is 1/2. Is that all right? Ayush? So you can do the same exact thing with the 45 degree angle. The difference is with a 45 degree angle, I'm going to draw it off to the side because there's no way I can draw it again here. Your 45 degree angle rules are that to get from your leg to your hypotenuse, you multiply by the square root of 2. So to get from the hypotenuse, which we have, to the leg, we divide by the square root of 2. And then in calculus, you really don't care if you have a square root in the denominator, but before that you do. So in pre-calc, we want to just rationalize that. So multiply the top and bottom by the square root of 2, and lo and behold, you get that square root of 2 over 2, and you get the square root of 2 over 2 down here as well. So that's where that 45-degree angle came from, square root of 2 over 2, square root of 2 over 2. Okay. And then if you look at the 60-degree, well, the 60-degree is fun because I could sketch a 60-degree angle and do all that work again. But if I'm a little bit more kind of with it on this, and some days I am, some days I'm not, but if we look at that 45-degree angle, that 45-degree angle, that terminal side that's 45 degrees, happens to be your y equals x line. And your 30-degree angle is 15 degrees away, and your 60-degree angle is 15 degrees away as well. So the neat thing is that this is a perfect reflection over y equals x. So if my 30-degree angle has a coordinate square root of 3 over 2, comma, a half, my 60-degree angle will have the swapped coordinates. So you can think of it either way. I just love the fact that your 45-degree angle is your y equals x line. And we just finished doing inverses. So it's just a nice little neat thing that you can do. So that's it. So the last thing that I think you guys need to kind of brush up on were right before that handwritten worksheet that I gave you on page 20, where I gave you those gray squares that we had to kind of figure out, where I gave you like negative m comma negative n. Like if theta passes through the point negative m negative n, find sine theta, find cosine theta, and then I got a little crafty and then said find the sine of theta plus pi over 2, theta minus pi over 2, things like that. So those are also going to be things that you need to know. And I did say that this is on the unit circle, because if I didn't say that, then you wouldn't be able to do it, or it'd be a little bit more complex. So sine theta is equal to, in this case, it's on the unit circle, so negative n. Cosine theta would be negative m. Sine theta plus pi over 2, if we think about it visually, what sine theta of plus pi over 2 is, we're looking at the fact that negative m comma negative n, let's say, lies right here for theta. So that's my theta angle. And if I'm adding pi over 2, it means I'm moving in a counterclockwise direction. If I were to subtract pi over 2, I would be moving in a clockwise direction. So I'm adding pi over 2, and pi over 2 again is 90 degrees. And what happens with that is negative m, negative n, is the distance that you move along the x-axis and the y-axis get flipped. So now you're moving the y distance along x and the x distance along y. So you're actually swapping these. And we're not just swapping them, we are actually saying, oh, well, we've moved into the fourth quadrant. So we're at the positive and negative. So the sine of theta plus pi over 2 would be negative m. I do, Varshini, I am very sorry. I do not have 86 from page 390. I don't have the book with me. So if you can kind of, there is no graphing, Evan. No, I have not done graphing with you yet. Sorry, I'm just shooting a email to someone too. It says find the exact value of tan of 60 degrees. Yeah, oh yeah, you can get one like that. That's not bad. So tan of 60 degrees plus tan of 150 degrees. You just do them separately. So the tan of 60 degrees, again, I'm thinking the sine over the cosine, and sine, so it's sine of 60 over cosine of 60. That's how I think of tan of 60 degrees. You could just actually look at your unit circle and look at your coordinates at 60 degrees, but for some reason, I know that this is what I have at 60 degrees. So I have the square root of 3 over 2 over 1/2. So I'm getting that tan of 60 degrees is just the square root of 3 plus, and then the tangent of 150 degrees. So what is that, a 30-degree angle in second quadrant? So 1/2 over the square root of 3 over 2. So we getting square root of 3 over 3. And because you're in the second quadrant, I think it's negative. Is that okay, Varshini? Students. So yeah, tangent's negative there. Let me know if it's not okay. Okay. So yes, you can do them. You would just do them like individually. And then I could probably make it, I would accept this, but I could, I mean, you could get it a little bit nicer, nicer depending on who you are, what you think. You could actually rewrite it as 3 square root of 3 minus the square root of 3 all over 3. So you actually could write it as 2 square root of 3 over 3. I think would be the best way to do it to get a common fraction. Yes, Ayush, you have a blank unit circle on the back. It's only a 1-page quiz. There's a front side and a little bit on the back, and then the unit circle is on the bottom of the back. And if it worked out nicer, could we have added the tans? I don't know what you mean. Smarthy, what? I don't know what you mean. I'm sorry. Can you go over the periodic properties? Yes, I can. Kelly and Lucy. Thank you. Like the tangent of 210. Like tan 60 plus tan 210? Sorry. Don't do that. Tan 60 plus tan 210. I don't think I am totally getting what you're asking, Smarthy. So, because this one worked out okay. Once you got common denominators, it didn't look too bad. I'm just waiting on you, but she wants to add the degree. Oh, no. Do not add the degrees. If I give you 2 trig functions with degrees in them, you're not allowed to combine them. So that was a good question. You cannot take tan 60 and tan 150 and make it tan 210. You have to do tan 60 on its own and tan 150 on its own. Yeah, trig functions don't work that way. Thank you. The periodic functions are your sine, cosine, cosecant, and secant of theta plus 2 pi k. Murphy, what are you doing? Oh, you are silly. All right. Sine theta, cosine theta, cosecant theta. I don't even know if I'm writing these in the same order. Okay. So your periodic functions say that you can rewrite sine of an angle that spirals more than once around the unit circle or around a circle. You can rewrite it by taking away that 2 pi k. So k is an integer. So 2 pi, 4 pi, 6 pi, 8 pi, 0, negative 2 pi, negative 4 pi, negative 6 pi. So any of your 2 pi's or multiples of 2 pi's. You can just rewrite it as just sine theta. Same goes with cosine, cosecant, and secant. Tangent has a period of pi. So tangent and cotangent, theirs is going to be theta plus pi k. And that's going to be equal to tan theta and cotan theta. So the tangent and the cotangent, the only difference is those periods are pi. So technically, I could look at tangent of 7 pi over 6, just like it were tangent of pi over 6. So hopefully that was helpful in how the periodic functions work. And yeah, Kelly, domains and ranges, I just think that they're nice to know because you can remember that like sign can only go from -1 to 1. So when I give you the point 3 comma 4 and you get sine theta equals 4, you should have an alarm going off in your head saying, no, 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 that can't happen. Sine has to be between -1 and 1. So that's why the domains and the ranges are helpful and that they're kind of nice. -4 is in radians. If I don't give you a angle measurement in terms of angles, like radians, degrees, gradians, you can assume it is in radians. So -4 is -4 radians. And the best you could do, Sumana, without a calculator is to write it as cosine of -4, comma, sine of -4. And that would be your coordinate. If I did allow you to have a calculator, you'd probably want to know what those values were, just because it's nice, again, to make sure that those numbers are smaller than 1 or negative, between -1 and 1. So this is it when it comes to the stuff that you really need to know. Again, I would go back to page 20, that handwritten worksheet in the workbook. Anything that is no calculator is a good question that I could ask you on the quiz. And just a reminder that I could ask you for the sign of, like if I gave you that negative, I don't remember what it was, so hold on, -m, -n on the unit circle, I could ask you for something like the sine of theta plus 3 pi over 2. And just a reminder that 3 pi over 2 is 270 degrees. So you could actually look at it as the sine of theta minus pi over 2, minus 90 degrees, or reverse the direction. So just a helpful hint that 3 pi over 2 is the same. If you add 3 pi over 2, it's the same as subtracting pi over 2, and vice versa. And then if you add just pi or subtract pi, all you have to do is change the signs of the points. You don't actually change the coordinates. You don't swap the coordinates. So if I asked you, let me give you this one first. So this is equivalent to sine of theta minus pi over 2. And again, if I were to think of that, minus means I'm going in the negative direction, which would be that way. So my point would be at anytime I add or subtract 90 degrees, it's NM, and I am still on the negative here. So the sign would be M. Okay. Now, if I asked you for the sign of theta minus pi, you're subtracting 180 degrees. You're in reality just turning this paper 180 degrees, so it's upside down. And it doesn't matter which way you turn it. If I add 180 or subtract 180, it's going to be upside down regardless. So for those ones, I just want to remind you that if your original coordinates were -m, -n, the minus pi is going to make your coordinates at m, n. Both signs change, but you do not swap. So the sign is going to be n. Okay. All right. Sorry, I wasn't looking at this. Pythagorean identities, like the sine squared plus cosine squared is equal to 1, you use to show that a point lies on the unit circle. The other Pythagorean identities I might just throw in there, like I might have somewhere on there, what would I have? Secant squared minus tan squared. Okay. So I might ask you, what is secant squared minus tan squared? So if tan squared plus 1 is equal to secant squared, I can subtract that tan squared. So secant squared minus tan squared is equal to 1. So that would be a way to kind of get those identities in there. That's the only way I'm going to use them right now. You can absolutely use them if I give you, like if I gave you the secant of theta, if I said secant theta is equal to 5, what's tan theta equal to? You could actually use your Pythagorean identity to find it. So that would be useful in that case. That's when I could use it or would use it. So again, if secant theta equals 5, and I probably also have to tell you what quadrant you're in. So let's say you're in quadrant 1. You could tell me that if tan squared theta plus 1 is equal to secant squared theta, sorry, I'm way down here and you can't see it, then you could plug in 5 squared is equal to tan squared plus 1. So you got tan squared is equal to 25 minus 1, 24, square root both sides. And you're going to get tan theta is equal to the square root of 24, which is what, 2 root 6, I think. And it's a plus or minus, but I told you you were in quadrant 1, so it's definitely a plus. Remember that when you square root, anytime you're square rooting and you have a variable involved, you got to say that it's a positive or a negative. In this case, it's positive because I told you it was quadrant 1. So Kelly, that's one specific instance where you could use the Pythagorean identities. Some people choose not to use them at all. They actually just sketch triangles every time, and they use the Pythagorean theorem. But technically, if you're using the Pythagorean theorem, you're using the identities. You just might not know it. So that's it in a nutshell of what my expectations are of you. I would, again, if you have not looked at section 6.2 and 6.3 at all, you might want to do that, because looking at just worksheet 20 is not good enough for most of us. So I would just suggest you go through some of those problems. Those are practice problems that I've assigned. So that would be my suggestion. And then that's about it. Ayush, did you record it? If Ayush is even here. Huh. Okay, good. Even and odds, yes, you definitely need to know your even and odd identities. They are definitely helpful. 8K or 8I in the workbook, please. Sorry, Riley. Yes, I did record it. 8K and 8I. Pretty much the same. Okay. So, Riley, you're going to have to, as best you can, tell me what 8K and 8I said, because I left my worksheet at school. So 8K and 8I. Can you kind of write that for me? I'm sorry. Unless Riley's not here anymore. Oh, you're here. I can see you. So if you can just tell me what 8K or anybody, if anybody can tell me what the worksheet 8K and 8I said. Secant of 3 pi is pi, Riley. Secant of 3 pi over 2 minus s. Secant of 3 pi over 2 minus s. Sorry, I'm making fun a little bit. I love you. All right. So what was the original coordinates, Riley? Sorry. I think they were actual numbers, weren't they? -7/25 and 24 25ths. Thank you. All right. So secant of 3 pi over 2 minus s. Riley, would you use the negative s or would you factor in the negative out? Because I'm going to do it the way you would feel most comfortable since you asked. You would factor it out. Okay, so secant of negative s minus 3 pi over 2. Is that correct so far? Is that how you would have factored it out? Okay, good. All right, so secant is secant even or odd? Even, okay? So because secant is even, if you have secant of a negative angle, you can write it just as if that negative weren't there. So secant of s minus 3 pi over 2. And I don't really like working with 3 pi over 2. I'd rather work with just pi over 2. So I'm going to look at it as secant of s plus pi over 2. Is that all right? So at that point, what I'm going to do is I'm going to look at the fact that my original coordinates were negative, negative. So I'm just going to sketch it quickly. That's where my negative, negative would be. And I'm adding pi over 2. Adding an angle means you're going in the positive direction. So here I am now. I was in the third quadrant. It means I'm going to be in the fourth quadrant. So when you add or subtract 90 degrees, your coordinates swap spots. So now my x is my y is my x. And because I added, I am now in the fourth quadrant. I am in the positive x but negative y. And then all I have to do at the end is find the secant of it. So the secant is a reciprocal for cosine. So my secant should be 25 over 24. Hope that's what I had on my worksheet. Please explain even and odd identities. Okay, I will. All right. So Ayush, even and odd identities are, you only actually have two identities that are even, and that's your cosine and your secant. So what it says is that cosine of any angle of the cosine of the negative of that angle would be equivalent to just cosine of that angle. And then secant is the same way. Your other four identities are odd identities. And I kind of gave you a visual of what it is because the proof for it is actually a more algebraic proof. And they actually get into, I think they use the sum and difference formulas for them, and we don't know those yet. So what I showed you guys in class was if you think of an angle theta, and we're going to call that point that theta, the terminal side passes through, A comma B. If I'm looking at negative theta and what that would look like, well, that's just a reflection over the x-axis. So that would be A comma negative B. So if I look at what's happening to sine theta is equal to B. Sine of negative theta is equal to negative B. So just a reminder of our even and odd functions. If we have f of x, right? If we input f of negative x and our result is negative f of x, it's said to be odd. And that's what's happening here. If I input f of x, I get b. If I input negative x or negative theta, I get the opposite of b. That output is opposite of the original. That's said to be odd. So that's kind of the visual sketch of why that happens. And then if I look at cosine theta is equal to A. If I then look at cosine of negative x or cosine of negative theta, notice that my output is still A. So it's exactly the same as the original. That's why it's even. So you can look at the same thing for tangent. If you look at tangent, it's B over A. The negative theta is negative B over A. So again, the result is the opposite of the original function. So hopefully that helped, Ayush. And we will revisit odd functions again. I don't know, like questions 10 maybe? you know me though, I put A's and B's and C's on it, so I'm not sure. I know that it's the whole front of a page and then maybe 1 or 2 questions on the back. So it's like a page and a half, but it's only one piece of paper, Varshini. Do you guys have any more questions? My evening was wonderful. Thank you for asking, Ben. It was good. Yeah. My car, oh, my tire. Oh, that got fixed that day. I came home that day and got my tire fixed. Yeah, my car is as fixed as it's going to be for a 2000, what is it, 2009? 2009. I got it in 2008, but it's a 2009. So, yeah, it's all right. I can't complain. It got me to school today. Hopefully it will get me to school tomorrow. That's a good year. How old were you guys in 2009? Oh, you were babies. I'm getting older. 8. Oh, 8. That's awful. My son's almost 8. He's 6, but he's almost 8. So I think we're good, or I'm good. I'm hoping you guys are good too. I am always available. The only time I'm not available for Flex is if I'm not in school at all. So you can always count on me to be there during Flex. So you can come stop by and ask me any last minute questions that you have during Flex tomorrow if you want to do that. Hopefully this was a nice little review after a nice restful vacation. So, or not restful, but I hope you got some rest. And I will see some of you for the first time tomorrow, and E-Block, I'll see you last block. Have a good night. Go to sleep early and eat a good breakfast before you come to school. Stay warm.